Hello everyone again and welcome to the Dajo Merit YouTube channel Science Institute, and it's truly a pleasure to have you here. And please, before we jump into the Suzuki coupling reaction part 4, please don't forget to hit the like. By that way others can actually get opportunity to check out these videos, and also subscribe because subscribing is free. So let's jump into this by looking at Suzuki coupling part 4 of our final phase of the Suzuki coupling videos. And in this video we're going to be focusing on this particular type of reaction, which involves Aryl-Aryl cross coupling. And in here we're going to explore some interesting things involving this particular reaction. And before we jump into this, we're going to actually step a little back to review all the things we've done and see how this all comes together in this final use of the Suzuki coupling reaction. So previously we looked at hydroboronation of octane, and in this particular reaction we know that the boronate comes in contact with octane, and this is done in the presence of heat and water. And once this reaction leads to a complex, which we'll talk about very soon, this actually comes in contact with another complex that actually had already undergone oxidative addition reaction, where in here we have a zinc-violin bromide, which is a form of alkyl halide, and this is actually reacting in the presence of our catalyst, which is the palladium complex. Using a base, this actually leads to a little bit of a transmetallation that produces intermediate complex that then results in the formation of our specific product, which is a specific stereo controlled product of EZ diene. And on the other side we built on this, where we focused on the stereo controlled synthesis of the EZ diene, where we looked at a specific example involving the alkaline bromate, and this boronate is actually going to be reacting in the presence of the violin iodide, and this once is done in the presence of our catalyst, which is palladium phosphanes, and a very strong base, which is called the sodium ethoxide. This actually leads to a really well directed EZ diene product. So looking at this, looking at the general mechanism of both reactions, first off we have our boronate, and this is going to be reacting in this case with a form of an alkyl group, and this actually in the presence of heat. This leads to a reaction called the hydroboronation, and from hydroboronation we produce our intermediate product, where one of the alkyl actually loses a pair pi bond, and from there on this alkyl boronate that is formed actually is going to be later used after we have our palladium catalyst forming a particular complex during oxidative addition with our aromatic violin halide. And through this particular process, after forming this oxidative addition product, we actually have this particular reaction in the presence of a base acting on the alkaline boronate to actually form our side product, which we don't really care about. And this side product then leads us to the main intermediate product complex that through transmetallation leads to the formation of this particular new sigma bond that would then be reformed by a really quick reductive elimination step, where our final product is actually shown with a sigma bond created during this particular process. And take note here that in some cases this leads to a stereo controlled product of the EZ diene. So in this particular video we're going to look at Suzuki coupling that is actually often used in Aryl-Aryl cross coupling, and this will actually lead us to an example, which is an overall reaction where we have our Aryl boronate, and this particular reaction is going to be reacting with a specific Aryl halide, which in this case is iodide. And we notice here to be seeing our Aryl group. So we have two alleles, one from the boronate and the other one from the halide, and this is going to be done in the presence of our catalyst, which is palladium phosphine and DMF, and also a really strong strong base, which is potassium phosphate. And in this case, this leads to our product where we notice to see two alleles coming together, forming a new sigma bond, and we notice that this new formation of bond is actually shown to be a 3-ortho substituent noticed around the newly formed bond. So looking at this observation, we see some interesting things that actually plays out, like steric hindrances that actually leads to a product that is actually specific in the positioning around the allele rings. We're going to look at the mechanism 1 in here, where we're going to see the mechanism of that reaction, and the mechanism involved first, starting with our catalyst. We actually going to be starting with palladium 0 and in the presence of our allele halide. In this case, it is called the allyl iodide. This actually is going to perform oxidative addition that then leads to a formation of our complex, which increases the oxidation number of our complex to palladium 2. And then in the presence of a very strong base, our base dissociates in aqueous solution, forming phosphate. And from there, phosphate interacts with our boronate. And from there, this through transmetallation, phosphate interacts with the boron in that particular part, and then we have the cleavage of our boron carbon bond to form a palladium carbon bond, therefore kicking out our iodide, and then we actually create our complex, which is still palladium 2. And in here we notice that we have a new carbon palladium bond, and this is actually side to side with the other allyl group. So in this particular path, after transmetallation is occurred, we notice sterically demanding process that actually directs our formation of a new bond to the third position, which is around the ortho regions. And during reductive elimination, that gets our catalyst back to its original oxidation number of 0, we actually get to our product by the breaking of our palladium carbon bond to the formation of a new carbon-carbon sigma bond, and then we have a carbon palladium bond breaking off and becoming a lone pair on palladium, or goes back to palladium, therefore resulting in the formation of our product, which in this case is the formation of a fresh new sigma bond that is actually producing a yield that is 85%, which is really incredible. So after moving through that, we look at another example here, and this example is going to involve aromatic heterocyclic couples, and this involves looking at regions where we actually introduce not really carbon, but now something quite interesting, like other hetero atoms like nitrogen or oxygen or sulfur. I actually remember in my lab back then, we actually used sulfur ring. Well, almost everywhere was sulfur, but it was pretty cool to see how that actually played out in various interesting reactions. Kind of smells a little bit, but it was pretty fun. I'll put it that way. But anyways, what we notice is that we have two positions of the pyridine, and what we notice in this case is that this actually leads to our complex to be overall, or compound to be overall aerophilic, and this is going to be coupling with our specific halides or boronic acid aromatic alleles. And what we notice here, of course, is that to ensure that cross-coupling occurs, we actually would try to prevent dimerization. So during this particular step, we are actually satisfying these particular conditions through using our specific reactants on one side in here, which are the catalysts, which are not reactants, but the catalyst is going to be involved. And also we have a couple of strong bases here, most especially potassium oxide, and in the presence of a solvent, benzene, while on the other side we look at, this time we're using tert-butyl oxide, which is going to be a really strong base to be involved in this particular reaction. And then we are going to produce our main product for the left reaction, where we have 56% yield, while on the other side here for the right reaction we produce our product, which is going to be around 83% yield. So let's look at a summary of the mechanisms in terms of those two reactions. So first is that we introduce our catalyst, and then our catalyst during oxidative addition changes its oxidation number from 0 to 2 plus, and this is done in the presence of our specific halide. And this halide is going to be mainly looking at bromide, and bromide is going to be involved alongside the specific aromatic heterocyclic compound. This heterocyclic compound here would then lead to the formation of our specific complex, and from there onwards we actually have the next reaction, which is going to be involving our specific base through transmetallation, where our base comes in contact with our boron, and this boron is going to be breaking off its carbon bond with its to form a carbon bond from the aromatic heterocyclic compound to that of the palladium, and then we kick off our bromide, and this actually leads to our side product, which we don't really care about. It's going to crashes out the solution. However, we actually get our intermediate product complex, which is going to be two heteroatom aromatic compounds, and this will then lead to our specific reductive elimination, where finally we have the formation of a new sigma carbon-carbon bond that is formed, and we see our two products, and these two products actually shows that on the left side we generate a 56% yield, while on the other side 83% yield. So that's about it for this particular video, and looking at everything involving our specific Suzuki coupling reaction and how this actually plays a huge role in the Aryl-Aryl cross coupling. This particular reactions in depth, the mechanisms involved, and why this is really crucial, mainly due to the intermediate step, which is a transmetallation, where we inject a strong base to actually speed up that particular reaction, and then we also look at how those allyl groups are attached to both the boron and that of halide. So those are the things to keep in mind when you're dealing with those kind of reactions in organic chemistry. So all the same, thanks for following me. Truly appreciate it. Hit a comment down below. Let me hear your thoughts about any questions that you might have, and see you all on the next one. Stay smart as always, and believe in yourselves.